ATM service, then we will search for the closest ATM or a closest restaurant or any other service center like okay, petrol station or okay, any other facility. So Google Maps, what it does actually, it gives a shortest path from your location to that closest resource center. And if there's a lot of traffic is there on that first shortest path, then it will give a path which actually leads to, which takes you to resource center in the fastest way actually. Okay, so this is the one problem. But in geometric setting, actually, we cannot use this roads and path like that. So what we'll see actually, we will look at this uh, nearest service center in terms of a radial distance. Okay, so that is what is called a Warner diagram. Okay, let's see. We'll go back to this whiteboard and we'll take few examples and we'll see how we can define a Warner diagram. I'm sharing my screen. Yeah, everybody able to see this whiteboard?
Yes, sir.
Okay. So suppose you in olden days actually only services center used to have actually post office. Nowadays post office become a redundant or it's not that much useful nowadays for day-to-day activities. But in olden days, so post office is the one common resource center. So each and every town or every village used to have, and everybody used to go there for some purpose, other purpose. So this is what in literature it is called what is called a post office problem. So basically, in a city or in a town, there are the multiple post offices are there or any resource centers are there. Now the users are everywhere in this town. Now everybody want to find out which one is the closest post office. Of course, in this diagram, and this is the closest one. Then any other uh, service center or post office here. So here this how we can pre-process this given resource center. Resource centers actually we call it as a site. So given a n sites, we want to pre-process such that given any query point where user want to locate it, and you want to identify who is the which service center is closest, which is the closest post office. Okay, so if you look at this one, okay, we'll take a little simpler one. Suppose there is only one post office is there, and only one site is there. So everybody in that town has to go there. There's no alternative. Suppose there are two service centers are there, two post offices are there. Then people go to which post office, whichever is closest. How to find out? You take a perpendicular bisector between these two. All the people which are this side of this are go to this PI. Maybe we call it as a SI, yeah. And all the people which are this side are go to this side SJ. Okay, so here this bisector actually defines the region, okay, corresponding to SI and region corresponding to SJ. So this is clear, no? If you take any query point here in this region, obviously SI is the closest one. Is this clear?
Yes, sir.
Suppose let's take another situation where there are three sites are there. Then if you look at this, let's name them. And suppose if you take a perpendicular bisector between SI and SJ, it will be something like this. Okay, of course, this is passing through here. Let's keep it something slightly this side. So here, all the region which are this side of this bisector closer to SI than SJ. Okay, now you take a bisector between SI and SK. It will be something like this. Now, if you take this region here, all this region here, if we extend this, all this region is closer to SI than SK. Okay, so if you take the intersection of these two, okay, that means this region, all the points here are closer to SI than SJ and SK. Agree?
Yes, sir.
Any questions here? Okay, so similarly, if you draw a bisector between SJ and SK, it will be something like this. Of course, I'm not. You are able to see the screen?
No, sir, not now.
Now?
Yes, sir, it's visible.
Yeah. So I'm not extending this bisector, okay, between SK and SJ into the region of SI. Okay, intentionally I stopped at that intersection point here. So if you look at this region, so let's use a different color here. All the points here are entire region. If you take any point in this region, and SK is the closest site, then any other site here, SI and SJ. Yes? Agreed?
Yes, sir.
And similarly in this region also. So this is what is called a Warner diagram. So given a n sites, so we want to associate one region to each site such that, okay, any point in that region is closest to that corresponding site than any other site. So this is what is called a Warner diagram. Now let's take a beginning, first example what you have taken here. Okay, maybe you can redraw it once again. So we have some sites are there. Okay. Now, how the Warner diagram looks like? Simply you draw bisectors. See, I forgot to tell one point here. Intersection between the three bisectors. What is this point? This point is equidistant from the three sides. Yes.
Yes. It's the
So,
center.
uh,
Circumcenter of the circle.
yeah, this is the circumcenter of the triangle found by these 3 points. Okay. Yeah. Now you come here. Now we try to draw a Warner diagram for this one. Okay. So I try to draw it. Basically, I try to draw the bisectors. Yeah, it's becoming a little complicated here. There may be a bisector between these two. Okay. And bisector will be something like this between them. Mm. Yeah, I think this example became a little close to each other. So that's why actually the points become very close to each other. So, yeah. It is not coming nicely here.
Sir, maybe you can remove 1 or 2 points if it doesn't affect much.
Okay, let's see. Let's draw it from the other side. Yeah, something like this. Yeah, this 4 points are meeting here. Okay, this I want to avoid it, but actually the points are such that, okay, these 4 points are meeting at one location. Okay, it will be something like this. So if you look at this one, for n sites, there are n regions are there. One region is associated to each of this site. And if you take any query point, and we can know that actually if this query point lies within this region, then we know that this is the closest site. So this is what is called a Warner diagram. Okay. Now, before computing, any questions here? So before computing this Warner diagram, then how we can store this? What data structure is suitable to store this Warner diagram? In fact, Warner diagram is actually a partition of the plane into regions. So one region is associated to each site. So here all edges here are straight line segments, and vertices are there, and regions are there. So there is a one data structure, what is called a doubly connected edge list. So we use this data structure to represent this Warner diagram. Not only Warner diagram, any planar straight line graph. Okay, if you take a planar straight line graph which is embedded in a plane, okay, planar embedded straight line graph. So all of them actually can be represented using a doubly connected edge list. So we'll discuss this data structure with a very simple example so that it becomes easier to understand. So let's take a very simple with just only 3 vertices, V1, V2, V3, and say V4. And we have an edge and this is the phase 1 and this is the phase 2. So basically entire planar graph, a plane is divided into 2 regions, F1 and F2, by means of these 4 edges. So what we will do actually is we, for sake of convenience, we replace these edges by what is called off edges. So this is the E1. So E1 is replaced by 2 directed edges, okay, off edges. Okay. Similarly, this edge, this is E2 in this one, this is E3, and this. Similarly, we replace other also in the same manner. No, I made this other way. Anyway, this is not a issue actually. Okay, this is F1 and this is F2. So basically, this is only for convenience actually. So in this doubly connected edge list, we have a 3 different types of records. There will be one record for each vertex, one record for each off edge, and one record for each face. So for vertex record, what will be there actually is vertex ID, and you can have its coordinates. Okay, and any one edge on which this is incident. Okay, and here this VI is incident on E11, E12, E31, and E32. In fact, we can choose any one of them. So what we can do is we choose a vertex edge for which this is the origin. So we keep this either V11 or E32. Any one is okay. Okay, instant edge. Similarly, V2 will keep 4, 2, and 3 will keep V4, obviously. So this is the one record for each vertex. And second thing is, and one record for each face. There are 2 faces are there, F1 and F2. So there will be one record for each of this face. Okay. So here, suppose if you have a face, so you take a this thing. This is one region. There is a hole in this region. Okay. So suppose if you take this region, this F1, F2, F3, and outside is F4. Okay. So we can look at this F1. Region F1 is bounded by this outer boundary. Okay, the F1 is bounded from outside by this one, red line. Similarly, this F1 is bounded by this boundary from inside. This is a hole inside the F1. And similarly, this is another hole inside the F1. So the region F1 is actually bounded by these 2 boundaries also from inside. Okay, these are internal components. And this is the outer component of this face F1. So in this face record, we keep a one edge which is incident on the outer component and one edge incident on the inner component, one for each one of them. So in this case, the 2 are there. So there will be one edge for each one of them. Okay. So here if you look at this outer component, and inner component. So F1, see in this diagram, this F1 region is, there's no outer boundary. So the outer boundary is nil. So this F1 region is bounded from inside. You can treat this as a whole. Inside this face F1. Okay. So for this one, we'll store a one edge which is incident on this one. Okay. We can keep any one edge. We'll keep an edge, off edge, such that the face is on the left side when you traverse on this one. Suppose if you take this E11, so if you traverse on this one in this direction, the face F1 is on the left side. So we'll keep this edge. Similarly, if you take a face F2, we'll keep a one edge which is incident on this boundary of the F2, such that, okay, the face is on the left side. So you can keep any one of them. So we'll keep this 4-1. Okay. And inner component, there's nothing is there, nil. So this is very simple, this thing. That's why actually there is a very simple information, not much information is there. Suppose if you take this one, okay, in this face, so we have to keep a one edge corresponding to outer boundary and one edge corresponding to inner boundaries, each inner boundary. Okay, so that comes an inner component. Is it clear? So now we look at this record corresponding to edge. So the vertex record and face record is very simple one. Then all the complexity is there in the edge records. Okay. So let's take this edge one. Okay. So we have a one record for each off edge. Let's take a first off edge E11. And for this edge, what is the origin? Origin is P1. And what is the twin edge of this one? So twin edge means other off edge corresponding to this edge. So here this other one is E12. Okay. Now, incident face. So on which face this edge is incident? So we have to see always what is the face on the left side. So F1 is the face one. Okay. And there are two more records. What is the next and previous? So now if you look at this off edge E11, okay, and you go to this destination of this off edge and you see what is there immediately next on the clockwise direction. So that edge is E42. Okay, immediately next in the clockwise direction at the destination vertex. Of course, here are two edges are there. Which one do you keep? Keep the off edge for which this is the origin. So we'll keep the E42, not E41. And the previous one, you look at this origin of this edge E11. and look at this edge, okay, previous one in the counterclockwise direction. Of course, here the two edges are there, E31 and E32, and we'll keep the edge for which V1 is the destination. That means we'll keep a E31. So this is the information what we'll keep it for each off edge. Is it clear?
Sir, can you please once explain the concept for incident phase?
Yeah, any other question? So we are keeping a one record for each off edge. So off edge is clear now. We have one edge in the graph. That edge is replaced by two off edges in opposite directions. Okay. So edge E1 is replaced by E11 and E12, which are in opposite direction between the same pair of vertices. Okay. Let's see the record corresponding to edge E11. So we'll keep this origin of this off edge, the V1 here. And what is the twin edge corresponding to E11? Other off edge corresponding to this E11, that is E12. Okay. And on which face is incident? So one side F1 is there, other side F2 is there. And for the edge E11, okay, one side F1 is there, other side F2 is there. So if you traverse in this direction from origin to the destination of this edge in the direction, whichever the face on the left side, that is what we will store. Okay, the F1 is the face on the left side, we'll store this one.
Okay. So what if there are multiple faces on the left side?
It's not possible, no? How it is possible on the multiple faces? Only one face will be there. See, if you draw any edge in a plane, there's one face on the one side, other faces on the other side. Only two are there. Is it clear?
So in the diagram that you drawn below, like where we have a bigger. Yes, sir. This one. So for the edge that is the bottommost edge, we have two faces on the left side, right? F2 and F3. Or we should write F1 in this case.
You're talking about some edge here.
The bottommost edge, which is
This
moving
one.
from left. Yes, sir.
See, there is one face. This is one face and this another face. So you look at the face on either side of this edge. See, in a graph, we are talking about instant vertex, instant edge, and instant face. So instant means which is instant on that face. Instant vertex.
Okay, sir.
Which is instant on the vertex. Okay. Clear?
Yes, sir. Clear.
Okay. Now, and after an instant phase, there is a next edge and previous edge. So these are very crucial information we need to store. This helps, okay, in many cases. See, what is the next edge of E11? Now you go to the destination of E11, that is vertex V2, and see which edge is on the next in the clockwise direction. Okay, clockwise direction, if you look at V2 for edge E11, see E11 edge as a destination V2, and look at this, what is the clockwise direction next edge? So here we have a E41 and E42 are there. So which off edge we have to store? We have to store the off edge for which this V2 is the origin. Why we have to storing is actually, see, when you travels from this E11 to E42 using the next one, this boundary of phase F1 we are reporting in this order, one edge after other edge. So that is the purpose of this storing the next one. You got it?
Yes, sir.
Similarly, you have to store what is the previous to the E11. So previous, you look at this origin of the edge E11 and look at the edge which is immediately from counterclockwise direction. Okay. Now here is the E31 and E32. Two off edges are there. You store the off edge for which this V1 is the destination. So that is the previous one. Okay. Clear? Okay, we'll fill this entry for another edge. Okay, let's see E12. What is the origin of this edge?
V2.
What is the twin edge of E12?
E11.
Face on which it is incident?
F2.
Yeah, F2 because F2 is on the left side of this edge in the direction. Okay. And what is the next here?
E32.
Yeah, so you have to look at this destination. At a destination, we have to look at one which is on the clockwise direction next. Okay, that is E32. Of course, E31 also there, but we keep the edge which is actually the for which this V1 is the origin. Okay, what is the previous one? So you have to look at this at origin. You have to look at this in counterclockwise direction. E41. Is that clear? Let's fill one more edge also. Okay. E say 21. E21. Okay, let's remove this red boundary. Okay, yeah. You can also remove this direction. Yeah, so E21, origin of E21 is V3, twin edge is E22, face on which this edge incident is F1. What is the next?
E22.
So at the destination, we have to see what is immediately next in counterclockwise direction. So E2. What is the previous one? At the origin, we have to see which is immediately next in the counterclockwise direction. So this is the information what is there in this one. So there will be one record for each of edge. All the complexity is there in the edge records. Okay. Is that clear?
Yes, sir.
Yeah. So suppose generally whenever we design any data structure, okay, we want to perform certain operation efficiently. what type of operations we can perform efficiently here. Generally, whenever this planar embedded straight line graph is given to us, okay, so what information we want to extract? Can you think of something? See, for example, you look at this Warner diagram itself. Suppose this Warner diagram is stored in a doubly connected edge list. What type of information we want generally?
Given some random point, which face it belongs to.
Okay. Yes. Anything else? Anything else you want to see? Suppose, okay, somehow we identified this face. Now, what is the boundary of this face? See how you report this face. You say that they report the face by means of its boundary. Okay. So, what is the boundary of this one? So, basically, given any face, how you report its boundary? Can this doubly connected edge list going to help us in reporting the boundary of any face? Suppose I want to output the boundary of this, say, face F1. How I can report it?
Sir, we can take the outer component and traverse next. And then inner component, the same thing.
See, when you want to output the boundary of a face F1, from the face record, we can get one edge which is instant on the inner component and outer component, one for each outer component. Okay, so there's no outer component. That means the open region. Only in the open region, there's a one hole is there, inner component, E11. So you go to E11, edge record, output this edge, and output the next one. Okay, output the next, output the next, output the next. Okay, so E11, what is the next of E11? E42. When you go to the E42 record, next of E42 is E21. E21. So next of E21 is E22. Next of E22 is E31. Next of E31 is E11. This way you can output the boundary of this one, okay, in the clockwise direction. Okay, suppose you look at the face F2. So you want to output the boundary of the face F2. Now, if you look at the face record, the F2 is the outer component E41. There's no any inner component. So now report this E41. So it is the outer component, outer boundary of this face F2. So from the 4-1, what is the next in the 4-1? E41. Next is immediately, which is on the clockwise direction at the destination.
E12.
E12. Similarly, what is the next of E12? E32. So we can output the boundary in this manner. Okay. Similarly, if you take a very complicated example like this, so that for F1, there is two inner components. One is for this one, other one is for this one. So there's a one edge corresponding to this, both of them here. Okay, two edges will be there. So you take one edge, output the boundary of one of them, and take the other one, output the boundary of other one. And for the outer component, you will have one edge of this one. Okay, use that one, output the boundary of this one. Okay, so basically, so we are reporting the outer boundary and inner boundaries of this phase F1. Everybody got it? Any questions?
So these vertex, phase, and edges records, we have to we have to program something to create that, right?
Which one?
We have to create a program. So these like these records for vertices, face, and edges. So like we have to compute all this.
Yes, this is the data structure. Yeah, we have to create
So,
the data structure. Yes.
So what is initially given to us in the problem? What is the exact data?
See, that is what you have to define actually. Suppose if you want to input, suppose you want to write a program for something, okay, you have to input data. In which format you are inputting the data? So you are inputting the data as doubly connected edge list for your program. Yes.
So no, so the WS linked list we will create, right? Not the input. I meant to ask, like, if we have to create the records for every edge, then
No,
we
see,
should have some.
Yeah. See, if you take any algorithm, okay, for the algorithm we have to give an input, no?
Yes, sir.
So in which format you are giving input is the issue. Okay, that's one thing. Suppose doubly see for some planar straight-line embedded graph, doubly connected list is given to us. Assume that one. So using this data structure, what information you want to compute? That's one question. Okay. So suppose look at this Warner diagram here. So suppose if you want to construct a Warner diagram, what is input to this one? The n sites with the coordinates. Yes.
Yes, sir.
What is the output? Output is the Warner diagram. Warner diagram is what? In which form you store it, which form you output it. You have to output the Warner diagram in some form, no? You look at the computer science point of view, the programming point of view. So your output of this algorithm is doubly connected edge list of the Warner diagram. Yes?
Yes, sir.
So here, see, what is your algorithm and what is input to the algorithm, in which form you are giving input is the issue, and what is the output, in which form you are outputting the your output is issue. So that you have to define. Okay. So if a planar embedded graph is given to us, what does it mean? So the planar embedded graph given to us in some data structure, some form. So that here we are assuming a doubly connected list. Okay. For example, okay, I understood your question actually. Okay, suppose planar embedded graph is given to us. Okay, suppose for example it's given as a adjacency matrix form. That is a graph, no? The graph is the generally we assume that input is given in the adjacency matrix or adjacency list form, no?
Yes, sir.
Okay. So adjacency matrix actually there's no any geometric data, there's no any geometric information is stored there. We cannot get any geometric interpretation of the data if your graph is given to us as a adjacency matrix or adjacency list. So even though this graph is given with various parameters, various attributes of the edges and the vertices in the form of adjacency matrix, we have to write a program or algorithm we have to design such that this adjacency matrix is converted into doubly connected edge list. So that whatever the queries we want to perform on this planar embedded graph, okay, outputting the boundary of any region, any other operation, so that can be done efficiently. Suppose this planar embedded graph is given to us as a adjacency matrix form. Okay, is it possible to output the boundary of any face efficiently? In this case, doubly connected edge list, we are able to output the boundary in the time proportional to number of edges on the boundary of this face. Yes?
Yes, sir.
Suppose the same graph is given as the adjacency matrix form. Is it possible to do it efficiently like that? No. Okay. So that is the reason actually what purpose, what are the operations we want to perform, and what data structure is suitable for us, we have to decide to output this efficiently. So from the geometric perspective, so we want to have a doubly connected list for the planar embedded graph to perform some geometric operations efficiently. Suppose this doubly connected list is given in some other form, okay, adjacency matrix form or adjacency list form, then that has to be converted to doubly connected list or any other efficient data structure so that your operations can be performed efficiently or required operations can be performed efficiently. Okay, is that honest? I answered your question.
Yes, sir. It's clear.
Okay, so this is the data structure. What is the useful to represent a planar embedded graph? And when you discuss this algorithm for constructing the Warner diagram, this algorithm is supposed to output doubly connected edge list of this Warner diagram. Okay, so we'll discuss these various properties and these algorithmic issues in next class. Okay, so we'll stop the class today here. Okay, any question? Okay, see you tomorrow.